All right, what's up, everybody? It's Dr. Rose here, back with his assistant, Dr. Porter, and today we'll be going over some more periodic table stuff. So let's get to it. That's where you come in.
Thanks. You're so good at this.
I know. I need to start a vlog.
Okay. No, you don't. Please don't. All right. So let's map out all of these trends on the periodic table. This is part of our midterm review, so make sure you know this for your midterm. All right. Keep track of these. Shielding, effective nuclear charge, atomic radius, electronegativity, and first ionization energy. You got it?
Mm-hmm.
All right. Sweet. Periodic table. Jump over here. So let's talk about shielding and effective nuclear charge. The two trends that explain all the rest. So when we talk about shielding, what do we look at? Rose?
That's a good question.
We look up and down groups.
Oh, I thought it'd be something really complicated.
So, no. If we're talking about shielding, we're talking about going up and down a group. So, as we go down a group, what happens to the shielding?
It gets smaller.
No.
Bigger.
It increases. So, we add a layer of shielding every time we go down a row. So, what about effective nuclear charge?
We go across.
We're going across a period. So, what happens as we go across a period to effective nuclear charge?
It increases.
Why does it increase?
Because that's a good question.
It increases because you increase the amount of protons as you go across a period. So, period 3, for example, 11, 12 protons, 13, 14, 15, 16, 17, 18. You increase by 1 proton as you go across a period. All right, so let's talk about atomic radius. What happens as you go down a group for atomic radius? Rose?
Does it decrease?
No.
Increase.
Why does it increase?
Because it's less protons.
Oh, take a look at this diagram. The darker we get, the larger the radius. So, as we go down a group, what are we also increasing?
The shielding.
Shielding. So, more layers of shielding means larger radius. So, more shielding means larger radius. Now, what happens as we go across a period?
The effective nuclear charge increases.
It does increase, but what effect does it have on the radius?
Does it get smaller?
It does get smaller. The attraction between the nucleus and valence electrons increases as you increase your ENC. So as you increase your ENC, it pulls that valence shell in closer and closer, making the radius decrease. Electronegativity, by definition, is what? I'm asking you. Electronegativity is the attraction to electrons in a bond.
So if they ask us,
So again,
and it's the one with the least amount of electrons or least amount of protons, that would be right.
no. Look at the definition. Electronegativity is the attraction to electrons in a bond. So you have 2 electrons in a bond. Think of it as a tug of war.
All right.
You're pulling on the electrons, I'm pulling on electrons. The atom with the higher electronegativity will pull the electrons closer to it.
So one with the most electrons will pull the most.
Most protons and least amount of shielding.
That's what I asked you the first time.
Okay. I don't know if that's basically what you said or not. I don't think it is, but we'll just go with that. All right. So, as we go down a group, what happens to electronegativity?
Shielding increases.
So, what happens to electronegativity?
I know this.
Well, just look at the diagram. It goes from 0.98 to 0.93 to 0.82 to 0.82 to 0.79 to 0.7.
So it decreases.
So it decreases down a group due to shielding. As we go across a period, let's do period 3 again. Let's just start with aluminum. 1.61, 1.90, 2.19, 2.58, 3.16.
It increases.
So it increases because the E and C increases. Now tell me, why do your noble gases not have electronegativity?
Because they don't require shielding.
Well, look at the definitions. Electronegativity is the attraction of electrons in a bond. Your noble gases typically don't form bonds. What does that mean about the two that have electronegativity?
They can form bonds.
Yeah, they will occasionally, krypton and xenon will occasionally form bonds, so they do have electronegativity. Was that your question, Joel?
Yeah.
All right, sweet. All right, so last one, ionization energy. So, ionization energy is energy required to do what? To pull an electron away from an atom. So how much energy does it take to pull an electron away? Well, as you increase the shielding going down a group, what happens to the first ionization energy? Rose? Take a look at the numeric values. 520, 495, 418, 403.
It decreases.
It decreases going down a group. Again, it's all about the attraction between the nucleus and electrons. So the more hold or the less hold that a nucleus has on electrons, the easier or harder it is to pull an electron away. So more shielding means less of a hold on electrons, easier to pull away. Takes less energy. Going across period 3, you notice that your first ionization energy does what?
It decreases also?
No.
It increases.
Increases. Increased E and C means increased attraction between the nucleus and valence electrons, means requires more energy to pull the electron off. So increased first ionization energy. All right, so back to the midterm review. That takes care of number 1. Number 2, compare magnesium, sodium, aluminum in regards to these trends. Well, first question you ask yourself, same group or same period? Same period. So what are we comparing?
We're comparing the electronegativity.
No.
Oh.
Between shielding and ENC, what are we comparing?
ENC.
Compare ENC. So, the highest ENC goes to aluminum. The lowest ENC goes to sodium. That means sodium is going to have the higher radius. So highest or largest radius. That means it will have the lowest electronegativity and the lowest first ionization energy. Yes.
Why does it have the lowest? Why does it have the largest radius?
So, because it has the lowest ENC, that means it doesn't pull that valence shell in close to it. Aluminum's going to pull that shell in really close, make it have a really small radius because of the higher ENC. Sodium has less protons, so that radius is able to sit out further away from the nucleus, making the radius larger.
So that means like the electrons are going to be closer. Is that what you're saying?
For aluminum, the electrons will be closer. For sodium, the electrons will be further away.
Because of the
Electronegativity, it's lower because, again, we're looking at the attraction between the nucleus and electrons in a bond. Because it has less protons, or sodium has less protons, it's not going to attract those electrons in a bond as much as aluminum would. And first ionization energy is the exact same reasoning. All right, compare lithium, sodium, and potassium. Same group or same period? Same group or same period? Jump back over to our periodic table.
They're in the same group.
All right, so they're in the same group. Same group. So what are we comparing here?
The shield.
Comparing shielding. Which one has the most shielding?
Whatever the lowest one is, which is sodium. Wait, potassium.
Potassium
Yeah.
has the most shielding. So, if potassium has the most shielding, that means it's going to have the larger radius. It's going to have a lower, or the smallest, electronegativity. And it's going to have the lowest first ionization energy. Again, it all comes back down to the attraction between the nucleus and valence electrons. All right, common ions found for the elements in group 1, 2, 16, 17, and 18. Group 1 has how many valence electrons? Group 1 has 1 valence electron. So what oxidation state is formed? It loses that 1 and forms a +1 oxidation state. What about group 2? Has 2 valence electrons, forms a +2 oxidation state.
How can you remember when the valence electrons? Wait, just look at the period.
Yep, just look at the group. Look at the group. All right, what about group 3? How many valence electrons? 3, and what is its oxidation state? +3. Jump over to 16. That's oxygen's group. 16 has how many valence electrons? 6. Instead of losing 6, it picks up 2 to have a -2 oxidation state. 17 has how many valence electrons? 7. Gains 1 to have a -1 oxidation state. Group 18 are your noble gases. 8 valence electrons. They're perfectly happy, so they don't gain or lose electrons.